Welcome to this lesson on explainable AI. The objectives of this lesson are to define model explainability, determine feature importance using Shapley values, and to determine feature importance using feature permutations. In this first section, we define the concept of model explainability. How do models make choices? We use machine learning models to help us make decisions. The models themselves choose between multiple classes in classification or between multiple output values in regression. How do the models make those choices? In the case of the decision tree, the classification of a sample is chosen based on its features. Each node in the decision tree asks a question about the sample features. And based on the answer to that question for that sample, the process flows through the tree until it reaches the bottom. At the bottom of the tree are the so-called leaves, which represent the possible classes for the samples. In the case of a random forest, we use multiple decision trees, thus the name forest, with a random subset of the features to be used for asking questions at each node, thus the name random forest. Each decision tree makes a choice about which class the sample belongs to, and then there's a vote taken and the majority wins. And that majority provides the final classification for a given sample. In the case of regression, the model chooses, or rather calculates, the response Y based on the features X of a given sample. These three models that we've studied closely are referred to as white box models because they provide easy to interpret insights on how the classification or regression value was determined. And last, in the bottom right, is the neural network. And the neural network is referred to as a black box model because it's not at all easy to interpret insights on how the classification was determined. Recall in a neural network, also known as a multi-layer perceptron, the features of a sample are sent through the network as input on the left, get multiplied by weights, summed together at each layer, and then sent through an activation function to fire an output value to the next layer. This process continues for each node at each hidden layer until the output layer, where a classification of the sample is made. In order to understand how such a model is making its choice, we need a specialized tool or approach. Why do we want to explain how models choose? Well, explaining AI is crucial for several reasons. One is transparency. Understanding how AI models make decisions helps users trust them more. When users comprehend why a particular decision was made, they can better evaluate the reliability and fairness of the system. Two is accountability. In many applications, especially those with significant impact on individuals or society, it's essential to know who or what is responsible for a particular decision. Explainable AI provides insights into the decision-making process, which can help assign accountability when needed. Three is compliance. Regulatory bodies often require transparency and accountability in AI systems, particularly in sensitive domains such as healthcare, finance, and criminal justice. Explainable AI helps organizations comply with these regulations. Four is bias detection. Understanding how AI models work allows researchers and developers to identify and mitigate biases that may exist in their data or in the algorithms themselves. Explainability facilitates bias detection and helps ensure fair and equitable outcomes. Five is feature selection. In high-dimensional data sets, such as RNA-seq data that we've been working with, we'd like to select only the most important features to train a model. Explainable AI is related to feature selection. Six is debugging. We can use explainable AI to debug individual incorrect predictions. Knowing which features to attribute to an incorrect prediction may shed light on the problem in the data pre-processing step, for example. And last is insights. Explainable AI can help us learn novel relationships and correlations between predictors and responses. What are some techniques in explainable AI? Some AI models have feature importance built into them. For example, in logistic regression, the coefficients of the regression model may be used as a crude form of feature importance. The larger the coefficient, the more it contributes to the model classification. However, this requires that the data first be standardized to the same scale because the magnitude of the coefficient may be proportional to the magnitude of the feature itself. Random forest uses a mean decrease in impurity to determine how much a feature separates one class from the others. Recall that impurity is a measure of how mixed the sample classes are at each node in the tree. Similar to logistic regression, in linear regression, the magnitude of the coefficients may be used as a crude indicator of the relative feature importance, again, as long as the features have been standardized to the same scale. There are two other techniques we will discuss in this lesson, namely Shapley values and permutation feature importance, which are agnostic to the model. A word of caution, correlation is not causation. Predictive machine learning models become even more powerful when paired with explainability tools, which identify the most informative relationships between the input features and the predicted outcomes. It is tempting to take this analysis one step further and assume that interpretation tools can also identify which features should be manipulated in order to change the responses. However, this can often be misleading. The reason relates to the fundamental difference between correlation and causation. In this slide, we see that sunny, hot weather causes people to buy more ice cream. And simultaneously, sunny, hot weather causes people to get sunburn. It would be a mistake to assume that an increase in ice cream sales causes sunburn. Of course it does not. The relationship between ice cream sales and sunburn is referred to as a spurious correlation rather than a causative one. Each of these outcomes are caused by the sunny, hot weather. In this section, we discuss determining feature importance using Shapley values. The concept of Shapley values originates from cooperative game theory and was developed by Lloyd Shapley in 1953, for which he won the Nobel Prize in Economics. Shapley values provide a way to fairly allocate the payout, or contribution, of each player to the coalition, considering all possible combinations of players. A combination of players is called a coalition, and in the next slide, we'll look at how Alice, Bob, and Charlie may have cooperated in different coalitions to win different prizes. At the end of those competitions, the question is, how do we fairly split up the prize winnings among Alice, Bob, and Charlie? The Shapley value is also known as the average marginal contribution. The slide shows the formula for how a Shapley value is calculated. It may look a little intimidating, but it's actually very intuitive when you unpack it. The Shapley value is calculated for each player I over all subsets S over n players. The Shapley value is the average weighted marginal contribution of a particular player in the game. The marginal contribution is the difference in the value of a subset containing player I minus the value of the subset not containing player I. In other words, the marginal contribution for a player is a measure of how much better or worse does a group of players perform when this player joins them. In the next slide, we look at a simple example. Here is a Shapley value example. In this completely fictitious example, imagine that these three players, Alice, Bob, and Charlie, used all possible combinations of players in multiple versions of the competition. Namely, when Alice, Bob, and Charlie, ABC on the left, play together, they win the $10,000 prize. If no one participates, then the payout is obviously zero. So the C of zero is a coalition of zero people, and no one's going to win the prize. So the payout is $0 per player. If Alice and Bob form a coalition of two, that's collection of A and B or coalition of A and B, they win $7.5 thousand. Alice and Charlie win $7.5 thousand, and Bob and Charlie win $5,000. If Alice plays by herself, that's the C of A, she wins 5,000, and so does Bob. If Charlie plays alone, he wins $0. Again, these are fictitious values, but we present them here just as an example. So to calculate the weighted average marginal contribution for Alice, we examine the payout for all coalitions she's a part of and subtract the payout for the coalitions she's not a part of. When we take the weighted average of these marginal contributions for Alice, we get 4.6K. Doing the same for Bob, we get a weighted average marginal contribution of 3.75K. And for Charlie, we get a weighted average marginal contribution of 1.25K. So based on these calculations, we conclude that Alice is the most valuable player, followed by Bob, and Charlie is the least valuable player averaged over all possible coalitions of players. These weighted average marginal contributions are the Shapley values. The higher the Shapley value, the more valuable the player is in the competition. So what does this have to do with machine learning? How are Shapley values used for feature importance in AI and ML? Think of machine learning prediction task as a cooperative game, where the features of the dataset are the players in the game. The goal of the game is to predict the output or target as accurately as possible. The payout or payoff in this game is the prediction error, or any other measure of prediction performance that the coalition of features achieves together. The Shapley value calculation takes into account the contribution of each feature. The Shapley value of a feature calculates its contribution by considering all possible combinations or subsets of features that could precede it and determining what extra value this feature adds beyond the subsets without it. The Shapley value calculates the average marginal contribution per feature, and specifically for each possible subset of features that does not include the feature in question, we look at the difference in the prediction output or model performance when the feature is added to the subset versus when it is not included. And again, the Shapley value is just the average of those marginal contributions across all possible subsets. One of the fundamental properties of Shapley values is that they always sum up to the difference between the game outcome when all players are present and the game outcome when no players are present. For machine learning models, this means that Shap values of all the input features will always sum up to the difference between the baseline or expected model output and the current model output for the prediction being explained. The easiest way to visualize this is through a waterfall plot, which is what we see on the right. Here we start with the background prior expectation for a function, which is the expected value of f of x, which is just the average f of x value. And then we go up vertically starting from x1, x2, x3. We incrementally add these features in, and we see what the value is. We see what adding that feature does to the predicted value f of x. We see that the expected value of the model, which is 2.215. Starting from the bottom then, if we add in the first feature x1 to the model, we see it contributes 0.01 towards the actual predicted value of f of x, which is 2.846 there on the top. Then feature x2 is added to the coalition, and its contribution goes in the wrong direction by 0.04. When the x3 feature is added to the model prediction, it moves the prediction 0.07 in the correct direction towards f of x. And we continue in the same fashion until x8, which contributes 0.92 to the model prediction f of x. Based on this example, we would say x8 has the best contribution and x6 has the worst contribution. One thing to note here is that these Shapley values are calculated for a particular input x to determine the feature importance for that prediction f of x. A different input x will have a different set of Shapley values per feature. So here's a summary of Shapley values and the pros and the cons. The pros of Shapley values are that they are model agnostic. Another pro is that they don't make any assumptions about your data distribution. And a third pro is that they have some nice properties. Namely, they are efficient. In other words, all the payout is accounted for with all the Shapley values. They're symmetric. In other words, if two features have the same importance, then they have the same Shapley value. And they're additive. If you have two different models, you can add their Shapley values together to get a cumulative sum across multiple models. The cons of Shapley values include it's very computationally expensive, even for small data sets. And if you recall back from the formula, we have to look at n factorial permutations of all the features. So n doesn't need to be very large before n factorial becomes very large. So it's computationally expensive. That's one con. Another con is it doesn't have any predictive power. In other words, it doesn't predict change in prediction when you change a feature value. It just gives you one value, and that's its feature importance. And the third one is there's some dependency on the choice of performance metric. So the quality of the Shapley value is only as good as the performance metric that you're using. Anyway, we're going to be using this SHAP tool, and you can see the website there, in our hands-on exercises. In this last section, we discussed using feature permutation to determine feature importance. What is feature permutation? Permutation feature importance is a technique used to measure the importance of individual features in a predictive model based on the decrease in the model's performance when the values of each feature are randomly shuffled. This method is model agnostic, meaning it can be applied to any machine learning model and is straightforward to understand and implement. Here's how it works at a high level. First, you train your model using the full data set and measure its performance, whatever the metric is, accuracy, an F1 score, root mean squared error, etc., on a held out validation set or through cross-validation. This initial measurement serves as the baseline performance of the model. Then you perform the feature permutation. For each feature in the dataset, you shuffle the values of that feature across the data points in the validation set, which breaks the relationship between that feature and the target. This means that only the values for one feature are shuffled at a time while the other features remain unchanged. With the shuffled feature, you then reevaluate the model's performance on the same validation set. You calculate the difference in model performance with the original unshuffled data and with the shuffled data for the feature. A significant drop in performance indicates that the model relies heavily on the feature that you just shuffled. Then you repeat. Often you can repeat this multiple times with multiple different shuffles, and that's how you get ultimately your feature importance. Here's a feature permutation example. In this slide, we compare the residuals, which are the differences between the predicted values and the actual values, for a non-predictive feature on the left and a predictive feature on the right. On the left side figure, we observe that permuting a non-predictive feature does not significantly degrade the model's statistical performance. The change in model performance, here we're using mean absolute error, is 2.53 minus 2.49, or 0.04. This 0.04 residual is not statistically significant. The p-value is 0.15. We're looking for anything below 0.05. From this, we interpret that the feature we permuted is not important in the overall model predictions. On the right side figure, we observe that permuting a predictive feature breaks the correlation between the feature and the target, and consequently, the model statistical performance decreases. The change in model performance, again, mean absolute error here, is 0.51 minus 2.28, or negative 1.77. This negative 1.77 residual is statistically significant. The p-value is 0.00001. From this, we interpret that the feature we permuted is important in the overall model predictions. And here is a summary of feature permutation. Some of the benefits or the pros of using feature permutation it's also model agnostic, and it also does not make any assumptions about data distributions, and it's easy to implement and it's easy to understand. The cons are, one is that random shuffling can lead to misleading results. Because how you shuffle the features, it could lead to misleading results. It's also computationally expensive for large data sets and complex models. And it also, the quality of this feature importance using feature permutation depends on your performance metric and which one you've chosen. So scikit-learn has a permutation importance built into it, and that's what we'll be using in the hands-on exercise. And that brings us to the end of this lecture where we discussed feature importance and explainable AI, how to calculate Shapley values, and how to use permutation feature importance in our models to explain our results. And in the hands-on exercises, you'll use Shapley values and feature permutation and compare them to the built-in feature importance functions to interpret the results of your machine learning models.